And we're back with part 2 of chapter 4. So we learned some vocab in the last chapter about strong electrolytes, weak electrolytes, non-electrolytes. We saw the solubility rules. We saw the 7 strong acids and the 8 strong bases, and some vocab words like solute, solvent, and solution. Okay, so what we're going to do is we're going to keep trucking through our understanding of chemical reactions. So at this point, we have 4 different categories of chemical reactions we've talked about: combination, decomposition, and combustion, which came from chapter 3. And then we added precipitation reactions to our list. And a precipitation reaction is when we start with aqueous solutions, and one of the things we formed was a precipitate, which means solid. So we're going to jump to our next type, which are metathesis reactions. The textbook also calls them exchange. In previous chemistry classes, these would have probably been called double replacement or double displacement reactions. I'm just using the terminology that our textbook uses to be consistent, but it means the same thing. So metathesis means to transpose. Okay, that's where this term comes from. So what we're doing is the reactants and the products. Well, the reactants are made up of 2 either ionic compounds or an acid and an ionic compound. So things made up of a cation and an anion, a positive charge and a negative charge. And what happens are the positive charges and the negative charges of our reactants flip-flop. So silver starts out with nitrate, but it ends up with chloride at the end. So the positive charge, negative charge, the positive charge, negative charge are just going to flip-flop. Now, there's only one correct way to do this. A negative charge, well, I guess I should change colors here. A negative charge and a negative charge cannot make an ionic compound, right? We spent a lot of time in chapter 2 figuring out how to put ions together to make neutral compounds. You can't forget that. So when you start with 2 compounds, one has a positive and a negative, something, and they could be plus 2 minus, it doesn't matter what the charges are, but something positive and something negative, and the other compound has something positive and something negative. When we make our products, they have to also be neutral compounds. So the positive thing in the first compound has to be paired with the negative thing in the second compound. The positive thing in the second compound has to be paired with the negative thing in the first compound. We need to mix and match these, but there's only one correct way to mix and match them, and that's to make sure that a positive and a negative end up paired on the other side in ways that they were not paired at the beginning. Okay, so again, this is also called double replacement, double displacement. So this is the pattern that they follow. Now, the thing that we're going to have to remember, though, like this is the generic pattern, positive charge, negative charge, positive charge, negative charge. When we put together our products, we need to make sure that the charges actually cancel. So the positive and the negative might not be +1 -1. They might be +2 -1 or something. So we've got to put them together so the charges cancel. So I've made us a little set of steps for how to predict the products, because with this type of reaction, I can tell you what 2 things you're starting with, tell you it's a metathesis reaction, and based on these steps, you can tell me what the products are going to be. We also did this with a little bit with the combination and combustion reactions back in chapter 3. Like the combustion reaction, I can tell you what chemical we're burning, and then I was expected that you could write the balanced chemical equation for it. The combination reaction, if I told you what 2 elements that we're combining, you could predict the product and then balance it. So with metathesis reactions, it's just another one where it's fair for me to give you part of the information and expect you to tell me the entire balanced chemical equation. So here's how we're going to do that. Step 1. Identify the ions in the reactants. So there should be 4 ions here. There are 2 compounds. First compound, positive charge, negative charge. Identify what they are and what their actual charges are. Second compound, positive charge, negative charge. Identify what they are and then what their actual charges are. So we've got to find those 4 ions first. Then combine the cation, the positively charged thing from the first reactant, with the anion, the negatively charged thing, with the second reactant. Use the ionic charges to make a neutral molecule to determine the subscripts. So you got to put them together so the charges cancel. And then do this for the cation from reactant 2 and the anion for reactant 1. So here is a hint. Remember, when we're writing neutral compounds, it goes positive charge is always listed first, negative charge is always listed second. So when you write your new products, it's going to be the cation and the anion. And the cation and the anion. That's the order. For our products, we then need to add states of matter to them, right? When we write a balanced chemical equation, we have to have states of matter: solid, liquid, gas, aqueous. So we will be using our solubility rules to help us with that. You will use the solubility rules to determine if your new products, the things you just made from step 2, are soluble, which means aqueous, or insoluble, which means solid. And then lastly, you're going to balance the equation. At that point, it's not guaranteed that it's balanced, so check to make sure it's balanced. Those are our steps. Okay, so here's some helpful reminders. We're going to go through this. We're going to practice this. But first, remind yourself that we can't forget to write the state of matter. So solid, liquid, gas, aqueous on everything. We have to make sure we balance it before we're finished. And when we're predicting our products, you have to make sure that the products are always neutral. The positive charges cancel with the negative charges. So let's try this. Okay, so in this question, magnesium nitrate aqueous and sodium hydroxide aqueous, both are soluble ionic compounds. I could tell this from the solubility rules if I wanted to look. And we will be using the solubility rules here. I'm not going to have us refer back to that chart as we go through this, but in Canvas, there is a link to a PDF file that has the solubility rules on it. So those would be good maybe for you to reference as we go through this when I reference the solubility rules. Okay, so first, step one was to look at the compounds and figure out what the positive charge and the negative charge are in this. So here's compound number one. We have a positive charge and a negative charge. Well, the positive charge is going to be this. So what we need to do is recognize what it is and then write its charge. The negative charge is going to be this. Now, when we're identifying the ions, I don't actually care how many there are. Like, I don't care how many there are. I want to know, what is NO3? Well, NO3 is nitrate, and then we have to know its charge. It's -1. So same thing for the second compound. I need to identify the positive charge and the negative charge. I need to write them as the formula with the charge. And again, I don't actually care how many there are. I just want to know what's the positive and the negative and the positive and the negative. So this is what I came up with. Magnesium nitrate, it's made up of magnesium, which is found in group 2, so it has a 2+ charge, and nitrate, which is a polyatomic ion, has a -1 charge. Sodium hydroxide is made up of the ion sodium, which has a +1 charge because sodium's in group 1 on the periodic table, and hydroxide, which is a -1 charge because it's a polyatomic ion. We have to memorize that. And so what we need to do next is figure out what we're going to pair together. So the cation on the first compound needs to be paired with the anion on the second compound. And then the cation of the second compound needs to be paired with the anion of the first compound. And then we need to write these. And when we write them, we need to write them so the charges cancel. So for sodium ion to be paired with nitrate ion, we need to look at the charges. Well, sodium's a +1, nitrate's a -1. We need the charges to cancel. Well, doesn't a +1 and a -1 cancel themselves out? So that's going to be sodium nitrate. And then when I do this for my other scenario, I'm going to put magnesium 2+ and pair it with hydroxide -1, and I'm going to make a compound out of that. Well, magnesium's a +2 and hydroxide's a -1. By themselves, one of each does not cancel that out. I have 2 positive charges and only 1 negative charge. So I'm going to add another hydroxide here. That's going to be a -2, and this is going to be a +2. So that's what I'm looking for to make them cancel. So when I write this as a chemical formula, there's 1 magnesium, the 2 hydroxides. Now, when you're looking back at the original compounds, sodium hydroxide only had 1 hydroxide. Awesome. I don't care. When we're doing this, you need to just identify which the pieces are and then put them together. That's why I didn't care that there were 2 nitrates at the beginning when I was doing this. I'm going to erase that now. Okay, so what I'm going to do is I've just predicted my 2 products. This is a product and this is a product. So we can go ahead and write the balanced chemical equation. The 2 things we started with are reactants, or we can start writing our balanced chemical equation. Well, so much for planning my space well. Erase these things. Okay, so the things I started with are the 2 chemicals we were given, magnesium nitrate and sodium hydroxide. We were told they were aqueous, so I wrote aqueous. We predicted our products, magnesium hydroxide and sodium nitrate. Now, if you had written sodium nitrate first and magnesium hydroxide second, you're still correct. The order in which you write the products isn't important. It's how you wrote them. Like, it needs to be 1 magnesium and 2 hydroxides, and 1 sodium and 1 nitrate. Now, we have 2 steps left. We need to predict the states of matter of our products. So we need to grab our solubility rules. And for the first one, we're going to look up hydroxide on our states of matter, or of our solubility rules. And it's down in the insoluble section. And then we're going to look at the exceptions to see if magnesium is there. Well, the exceptions are the alkali metals, sodium, or lithium, sodium, potassium, rubidium, cesium. Magnesium's none of those. Or calcium, strontium, barium. Magnesium's not those either. So it's not an exception, which means it follows what other hydroxides do, which means it's insoluble. So I'm going to write an S after that. And then I check out, so there's my S. And then I look at sodium nitrate. I'm going to look up nitrate in the solubility rules, which is in the soluble section. I go to the exceptions, and there are none, which means all nitrates are soluble. So when something is soluble, we're going to say AQ. So that takes us through step number 3. Step 4 was to balance it. So we need to look, is this equation balanced? We'll just eyeball on this. Okay, 1 magnesium on the left, 1 magnesium on the right. 2 nitrates on the left, 1 nitrate on the right. Crap, it's not balanced. So I can make my little chart and balance it. I am going to kind of skip ahead here, and what I'm going to end up with is a coefficient of 1 and then 2 and then 1 and then 2. So 1 magnesium on each side, 2 nitrates on each side, right? Because there's a 2 right here. 2 sodiums and 2 nitrates. There's a 2 right here, so 2 sodiums and 2 hydroxides. So 2 sodiums and 2 hydroxides. So that's my balanced chemical equation. So it would be expected that I would tell you these 2 things and you could predict everything else. And those 2 things I wouldn't have included the 2 in front of the sodium. It would have been just like this question was given. So let's try another one. What compound precipitates when solutions of iron 3 sulfate and lithium hydroxide are mixed? First, write the balanced chemical equation. So, going back through our steps, step number 1 is to identify the ions in each of the compounds. So Fe2SO4 3 has iron and sulfate. So I need to write those down, and I need to write them down with the charges. So sulfate is SO4 -2. It's a polyatomic ion. Iron is a transition metal. So when I write down iron, it's going to be Fe, but then I need to write a charge next to it. Well, it's a transition metal. So we're going to have to do back what we did in chapter 2. Well, doesn't this compound have 2 irons and 3 sulfates? And with my sulfates, I know because I memorized the polyatomic ions, they have a -2 charge. So as a neutral compound, this has to have, so the total is going to be -6. As a neutral compound, it has to have the same number of positive charges, which means 6 positive charges. And those are going to be spread evenly between the irons, which means each iron has to have a +3. Okay. So those are the two ions. I'm going to have irons and sulfates are going to be my ions coming from this compound. And then my second compound, lithium hydroxide, well, Li, if I look at it on the periodic table, it's in group 1, so it has a +1 charge. And hydroxide, just like the last example, is a polyatomic ion with a -1 charge. So those are my 4 ions. Now I need to pair them up to be what my products are going to be. So I know that these 2 compounds are my reactants. What I'm trying to make right now are my products. So the positively charged thing from the first compound is going to be paired with the negatively charged thing of the second compound. And the positively charged thing from the second compound will be paired with the negatively charged thing from the first compound. So when I put lithium and hydroxide together, or sorry, lithium and sulfate together, I have 1 positive charge and 2 negative charges. Well, that's not going to cancel. So it's going to take 2 lithiums and 1 sulfate to make that happen. And then for my other compound, I'm going to be putting iron 3 ion with hydroxide. Right now I have 3 positive charges and only 1 negative charge. So it's going to take more hydroxides. So when I go to write these as chemical formulas for my products, it's going to be Li2SO4, right? 2 lithiums, 1 SO4. 1 iron to 3 hydroxides, so Fe parentheses OH3. So we've identified our 4 ions, and then we paired them up, making our charges cancel. Next is to find the states of matter. So I'm going to grab my solubility rules, and we're going to look up sulfate, which is in the soluble section. Look at the exceptions, and lithium is not one of the exceptions. Okay. So that means it is soluble, so aqueous. Now we're going to look up hydroxide, which is in the insoluble section, and look at the exceptions for that, which again, the alkali metal, so lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium. Iron is none of those, so it's not an exception, which means it's going to follow the hydroxide rule, which means it'll be insoluble, so I'm going to say solid. Okay. Next, I need to balance it. Looking at this, it is not balanced. So I'm going to have to make my little chart, count the number of irons and sulfates and lithiums and hydroxides. Now I am going to skip ahead, so if this would be a good time if you're worried about balancing, why don't you try balancing this? And then let's see if you and I agree on this, because what I got as my answer is a coefficient of 1 in front of the iron 3 sulfate, 6 in front of the lithium hydroxides, 3 in front of the lithium sulfates, and a 2 in front of the iron 3 hydroxides. It's awesome. So we've got our balanced equation. But if we go back and look at the question, it actually had another, it says to write the balanced chemical equation. Bam, right there. But it also said, what compound precipitates when solutions of Fe2SO43 and LiOH are mixed? So we're looking for the precipitate. Do you remember how we recognize the precipitate? It's the solid that we made. So it's a solid that's a product. So if we look at this, that's aqueous. This is solid. That is going to be my precipitate. So this reaction, which actually is going to be a prettier square shows up, actually falls under two categories. It is a metathesis reaction because it followed the trend for metathesis reactions, but doesn't it also follow the trend for precipitation reaction? So chemical reactions can be more than one type. It's both a metathesis reaction and a precipitation reaction. So if we backtrack to the previous slide, we look at this. This one is also a precipitate. This is a precipitate, and it's also a precipitation reaction. Okay. So I want you to try this one. So at this point, I would love you to pause the video, do the steps that we talked about, the 4 steps, to write the balanced chemical equation, and then go ahead and answer to yourself if you think a precipitate forms, and if it does, which one is it? So go ahead and hit pause, practice this. Once you've practiced, come back and hit play so we can go through it together and we can check our work. It's worth it to actually stop and practice here. These are going to be important parts of this chapter. Okay, so first we need to identify the 4 ions. So barium chloride, well, barium has a 2+ charge because it's in group 2. Cl as an ion is in the group 17, so it's got a -1 charge, so Cl minus. The potassium carbonate, potassium has a +1 charge because it's in group 1. Carbonate's a polyatomic ion and it's got a -2 charge. So those are the 4 ions that we're working with. Again, I'm not counting how many of each of them there are in the compound. I'm just identifying what ions are there. So the barium is going to be paired with the carbonate on the product side. And potassium is going to be paired with the chloride. So when I go to make these compounds, well, I know the 2 things that we're starting with are reactants. That's a reactant. That's a reactant. It calls them solutions, which tells me that they're aqueous. I could also use our solubility rules to figure out if barium chloride and potassium carbonate are aqueous or solids. So I just rewrote them with aqueous. And then my products, well, barium and carbonate. Well, barium is a +2, carbonate's a -2, so one of each works greatly. Potassium chloride. Potassium's a +1, chloride's a -1, so one of each. The charges cancel. Next, we need to look at our solubility rules. So we're going to look up carbonate, which is in the insoluble section, and then go through the exceptions. Barium is not an exception, so it is a solid. Potassium chloride, we look up chloride. It's in the soluble section. There are listed exceptions, and potassium is not one of the exceptions. So potassium chloride is going to be aqueous because it's soluble. And then next we need to look to see if this is balanced. Well, it's not. So to balance it, we're going to have to add a 2 in front of the potassium chloride. So that takes care of our balanced equation. This is our balanced equation. But the last step was, does a precipitate form? And then I'm asking you, if so, which one is it? So what do you think? Yes or no? Does a precipitate form? Well, we're looking for a solid. Did we make a solid? Yep. And the one that we made was barium carbonate. So that's our precipitate. This was a precipitation and a metathesis reaction. Okay. Let's try a couple more. So for this one, I want you to practice this one as well. I want you to read this question, go through the 4 steps to predict the products, write a balanced chemical equation, and then decide if you think a precipitate forms, and if so, which one is it? So hit pause, practice this. When you're done, come back, and we'll go through it together. Okay, so to go through this one together, potassium phosphate, K3PO4, is made up of potassium +1, so K+ ions, and PO4 - 3 ions. Zinc bromide is made up of zinc 2+ and Br- ions. So those are our, oops, I forgot. Sorry, pushing things. So let's go with green. So I have potassium and phosphates. I have zinc 2+ and Br-. Now Br- I knew was a -1 because it's in group 17. Zinc, you might be like, how the heck did you know that? I know it's in the transition metal section, so I could have figured it out from the Br-, the 2 Br-, but zinc is also one of those ions that's in the transition metal section, but always has the same charge. Okay, so zinc is always a 2+. So when we put this together, potassium and bromide are going to end up together on the products side, and zinc and phosphate are going to end up together on the products side. So when I go to write this out, first I'm going to write the reactants. So K3, PO4, aqueous, and ZnBr2, aqueous, arrow. So I'm going to put potassium and bromide together. So when I do that, K plus and Br minus is going to make, well, one potassium and one bromide. I'll have to look at the solubility rules, and when I do that, I look up Br minus, which is in the soluble section. Potassium is not an exception, so I'm going to write aqueous. And then I'm going to have to add zinc and phosphate and put them together. Well, one of each is not going to work on this because zinc is a 2+, phosphate's a -3. The lowest common denominator, I'm going to have to get to a +6 and a -6 to get these to cancel out. So to make that happen, it's going to take 3 zincs and 2 phosphates. So I look up phosphate in the solubility rules. It's in the insoluble section. Zinc is not an exception, so it's insoluble, so solid. So I've predicted my products. I found my states of matter, and my last step of balancing this is going to be to balance it. So if we look at this, it is not balanced at all. So what I normally like to do is start with the polyatomic ions, and the only polyatomic ion when I'm balancing here is phosphate. So I have 2 phosphates on the left and 1 on the right. So if I put a 2 right there, I got my phosphates balanced. So let's go ahead and balance our potassiums now. I've got 6 potassiums on the left, 1 potassium on the right, so I put a 6 right there. Now I can do zincs or bromines. It doesn't really matter. I've got 3 zincs on the product side and only 1 zinc on the reactant side, so I put a 3 right there. I have 3 zincs. Now I have 6 bromines on the left, and turns out 6 bromines on the right. So 2, 3, 6, and 1 are our coefficients. I cannot reduce that down any further. Last step is to determine if a precipitate forms, and if so, which one. There it is, because it's a solid. That's how I know I made a precipitate. All right, let's go for another one. Okay, so this will be our last one before we move on to something new, if that makes you feel better. Or not, I guess. So write the balanced equation for this reaction. So sodium sulfide and copper 2 acetate. So remember, again, the polyatomic ions that we learned back in chapter 2, they're not going anywhere, friends. So if you've forgotten them, you didn't ever become familiar with them, it's time to go back and feel better about chapter 2. So because I could also ask these questions by just giving you their names instead of their chemical formulas. So let's go through our steps. First, we need to identify the ions in the 4 ions we're working with. So sodium sulfate is made up of sodium, Na, and I look it up on the periodic table, it's got a +1 charge. The other ion is sulfide, so S. I look it up on the periodic table, it is in group 16, which has a 2- charge. Okay, the other compound is made up of copper, which I look on the periodic table as a transition metal, so it has a varying charge. We will come back to that, and we're going to add a charge there. But the next one is a polyatomic ion, acetate, and we need to remember that as a -1 charge. So that compound is made up of 1 copper and 2 acetates. Those 2 acetates add together to be -2. So the copper must be a +2. We did this back in chapter 2 when we were naming. So predicting what our products are going to be. Well, the positive charge here is going to go with the negative charge there. The positive charge here is going to go with the negative charge there. So we can go ahead and predict our products and write our equation. So I'm going to start with sodium sulfide, and I can tell from the solubility rules. I look at sulfide, it's an insoluble compound, but one of the exceptions are the alkali metals, which are lithium, sodium, potassium, rubidium, cesium, so it's soluble. And then copper 2 acetate. Acetate is in the soluble, that's a 3, section, and there are no exceptions, which means everything with acetate in it is soluble, so is aqueous. So I'm going to put sodium and acetate together. So Na plus and CH3COO minus, +1 -1. I look that up. It's soluble. Ooh, I'm not going to fit this on here as nicely as I hope. Copper 2+ and sulfide 2- are going to, well, one of each. I look this up on the solubility rules. This is sulfides are insoluble. Copper is not one of the exceptions. So when we look at this, the last thing we need to do is see if we need to do any work to balance it. So looking at it, well, on the left, 2 sodiums, on the right, 1 sodium. So it's not balanced. If we look, the sodiums and the acetates are the things that are not balanced. So there are 2 acetates on the reactant side and only 1 on the product side. So I'm going to go ahead and balance that first. So put a 2 right there. That also fixes my 2 sodium issue. So this is now my balanced equation. So I can give you 2 reactants for metathesis reaction and have you predict the products. You're going to need your solubility rules. You're going to need to remember how to put ions together and to know our steps to get through that. Okay, so all the equations, the balanced chemical equations we've looked at so far this semester, so between chapter 3 and chapter 4, all of them have been what we call molecular equations. They're written as molecules. Okay, so we're familiar with these. We've seen them. Okay, they look like this: plus charge, minus charge, plus charge, minus charge, plus charge, minus charge. Okay, so what's interesting about this, though, is this has not taken into account the fact that those strong electrolytes, when they're added to water, they don't actually stay as molecules, right? When they're strong electrolytes, 100% of them break apart into their individual ions. So molecular equations are not necessarily reflective of what's actually happening on, what's happening here. So we have ionic equations, which take into account the strong electrolytes, which are the 7 strong acids, the 8 strong bases, and the soluble ionic, it says salts, but soluble ionic compounds, the things from the solubility rules that are soluble. So those things in real life, once they're mixed together with water, they're not going to stay as compounds. They're going to break apart as ions. So an ionic equation is going to show that. So what we need to do to convert a molecular equation, which is what this is, I'm going to write E for molecular equation, into an ionic equation, is to identify those things. Find, are there any of the 7 strong acids? Are there any of the 8 strong bases? Are there any soluble ionic compounds? And recognize those as strong electrolytes and then break them into their ions. So for me, the first thing I look for are the 7 strong acids. So acids are things that start with hydrogen, and then the 7 strong acids are the 7 that we're supposed to memorize. I don't see anything that starts with hydrogen, so there are not any strong acids in this example. I'm not saying that they're not important. I'm saying in this example there are no strong acids. The 8 strong bases are those 8 compounds that have hydroxide in them. There aren't any of those. So to find, now we need to look for the soluble ionic compounds. Well, we need to look for ionic compounds, which we will recognize as having a positive charge and a negative charge. And if they're soluble, they are going to be ionic compounds that are aqueous. Now, don't immediately jump to, oh, if it's aqueous, it's a strong electrolyte, because weak electrolytes are weak acids, and those are always going to be aqueous as well. As far as you're concerned, all acids are aqueous. So aqueous does not equal strong electrolyte. Aqueous just means dissolved in water. Okay, so if it's an ionic compound and it is aqueous, then it is a strong electrolyte. So I see, so this is a strong electrolyte. This is a strong electrolyte. This is a solid, right? So it's not a strong electrolyte. This would be like a non-electrolyte. And this would be a strong electrolyte. So what we're going to do is we're going to take those 3 things that are strong electrolytes, that are either one of the 7 strong acids, one of the 8 strong bases, or a soluble ionic compound, and we're going to break them apart into the ions in which they were formed from, because that's what's the definition of a strong electrolyte. Once they're added to water, 100% of them break into their ions. So silver nitrate will become silver ion and nitrate ion separately. Potassium chloride will become potassium ion and chloride ion separately. Silver chloride is not a strong electrolyte, so it stays exactly how it is. And then potassium nitrate breaks into its potassium ion and its nitrate ion. So this is what we see. Every single thing in your balanced chemical equation has to have a state of matter after it. So silver nitrate was a strong electrolyte. Hold on a second, baby. So each of its ions need to become aqueous. Potassium chloride was aqueous, so each of its ions become aqueous. Silver chloride was not a strong electrolyte. It stays exactly as it is. Potassium nitrate was aqueous, so each of its ions are aqueous. Okay, so ionic equations. You start from the molecular equation. Identify the strong electrolytes, and then write the strong electrolytes the way they really exist, which are their individual ions. Now, when you go from a molecular equation to an ionic equation, it better still be balanced. Nothing gets removed when you go from a molecular equation to an ionic equation. Okay, now we were going to practice this, but before we practice it, I'm going to go to our 3rd type of equation, which comes from the ionic equation. Okay, so going to the next step, are the net ionic equations. So to form a net ionic equation, to get to that point, you first have to start with the ionic equation. So that means in the order to get to net ionic equation, you start with number 1 molecular equation, then turn that into a number 2, an ionic equation, and then turn that into a number 3 net ionic equation. Sometimes people think that they're super geniuses and they can go straight from the molecular equation to the net ionic equation. You can only do that once you're like really, really, really good at it. And I'm not doubting you at all, but let's start by doing all 3. Plus, when I ask these questions, I'm going to make you do all 3 steps. So might as well go in order. So here's an ionic equation. It's the ionic equation that we made in the last problem. So to turn it into a net ionic equation, here's what we need to do. We need to look for what are called spectator ions. Spectator ions, just like a spectator at a sport. So I'm a big Chiefs fan. So when I go to watch the Kansas City Chiefs, by the way, I was born in Kansas City. I've always been a big Chiefs fan. I'm not a bandwagon fan just because they won the Super Bowl. Oh my gosh, I watched them lose so much. Anyway, so when I go to a Chiefs game, when I go to Arrowhead, I'm sitting in the stands. I'm a spectator. Okay. As I watch the game, me being there has no impact on the game actually happening. Like, it has an impact in my life because I'm there, but whether or not I was sitting in the stands, regardless of how superstitious some people are, that would not have changed the outcome of the game. So a spectator ion is present, it's there, but it's not changing the outcome of the reaction. So in other words, it's not part of the chemical reaction. It looks the exact same at the beginning as it does at the end. It didn't change. So looking at this reaction, I see, oh my gosh, words, 2 spectator ions. So what I can do is I'm going to look at things. So silver plus aqueous, what I'm looking for on the product side. Does it look exactly the same? Well, there's silver, but now it doesn't say silver plus AQ after. It looks differently. So that's not a spectator ion. It changed. NO3 minus aqueous. Let's find it on the other side. Nitrate, nitrate. NO3 minus aqueous. Doesn't that look exactly the same? So that is a spectator ion. K plus aqueous. K plus aqueous. Find on the other side. K plus aqueous. Doesn't that look exactly the same? So it's a spectator ion. Cl minus aqueous. We look on the other side. I see Cl, but it doesn't look exactly the same, so it is not a spectator ion. So once you've identified your spectator ions, we have 2, nitrate and potassium. We cancel them out. Gone. They're gone. What is left is the net ionic equation. What the net ionic equation is a summary of exactly what reacted, what changed. What was the real life reaction that happened? In this case, potassium and nitrate could have been replaced with acetate and sodium, and I would have gotten the same result. They're just saying that they had to be present for the charges to cancel out. But in terms of the chemical reaction, they did not participate in the reaction. They were spectators. They watched it. Okay, so the net ionic equation is really breaking a chemical reaction down to the very specifics of what actually changed. It's the most useful thing. Okay, so here's the definition of spectator ions. We already talked about it, but there it is. They're the ones that are not participating, but are just watching the reaction. Okay, so I made steps for this as well. Step 1, to write a balanced molecular equation. So if I say, okay, write the net ionic equation of this, you have to start with the balanced molecular equation. I may have given it to you, or I may not have. So first of all, make sure you have the balanced molecular equation. Step 2, identify all the strong electrolytes to make an ionic equation, leaving the weak electrolytes and the non-electrolytes alone. Do not change. So if you recognize something as a weak electrolyte or a non-electrolyte, do not break it apart. If something is a strong electrolyte, you break it apart into its ions. You dissociate it. Okay. Then, to get to the net ionic equation, you're going to cross out anything that looks exactly the same on the left hand and the right hand side of the equation, which is, in shorter words, removing the spectator ions. And then rewrite what is left. Write the remaining stuff that was not crossed out, and that should be the net ionic equation. Everything should still be balanced at this point. If something is unbalanced, you screwed something up. Okay, so it is possible that at the end, the net ionic equation, its balancing can be simplified. So maybe it's a 2 and a 2 and a 2 are the coefficients, and couldn't I reduce that down to 1, 1, and 1? Well, that's possible when we get down to the net ionic equation, but it still needs to be balanced. So some helpful hints. You must identify the strong electrolytes. There's no way around that. Strong electrolytes are the 7 strong acids, the 8 strong bases, and soluble ionic compounds. You always have to show charges for any ions. If it's a neutral compound, you don't show the charge. It's not an ion, but it's an ion. You have to have a charge there. The reaction has to stay balanced, and you have to have a state of matter, solid, liquid, gas, aqueous, after every single thing. Okay, so we're going to try this. I've already given us step 1, where we started with our balanced molecular equation. We're going to pick up from there. Okay, so starting from the balanced molecular equation, and again, if this wasn't provided for you, we practiced earlier in this video how to come up with the balanced molecular equation as long as I gave you the two reactants. Find the 4 ions, figure out how they go together, put them together, solubility rules, balance. Okay, so what we need to do is recognize the strong electrolytes. So our strong electrolytes are either the 7 strong acids, the 8 strong bases, or soluble ionic compounds. So the first thing I look for are the acids because those are the easiest to identify. Looking at the 4 compounds here, none of these are acids, and I recognize that because none of them start with H. The 8 strong bases. Well, there are 8 specific compounds with the 8 strong bases. They all end in hydroxide. Not everything that ends in hydroxide is a strong base. There are only 8 of them, but none of these things end in hydroxide. So there are no of the 8 strong bases. So next are the soluble ionic compounds. So what we're looking for are ionic compounds that are soluble, and we can recognize if they're an ionic compound because they're made up of a cation and an anion. So usually a metal and a nonmetal, or a metal and a polyatomic ion, or a polyatomic ion and a polyatomic ion, or a polyatomic ion and a nonmetal, whatever. An ion, 2 ions, okay? And that they are soluble. So you can either check if they're soluble based on the solubility rules, or if it's already given to you, like this equation is, if it's an ionic compound and it's followed by aqueous, then as long as both of those things are true, it is ionic and it is followed by aqueous, then it's a strong electrolyte because it's a soluble ionic compound. All 4 of these compounds are ionic compounds. So calcium chloride would then be a strong electrolyte because it's an ionic compound and it is soluble. Sodium carbonate is a strong electrolyte because it is an ionic compound and it is soluble. Calcium carbonate is a non-electrolyte. Oops. It is an ionic compound, yes, but isn't it a solid? So it's not soluble. Okay. Sodium chloride is a strong electrolyte because it's a soluble it's an ionic compound and it is soluble. So calcium chloride, sodium carbonate, and sodium chloride. I'm going to have to break those 3 compounds into their ions, break them into their positive charges and their negative charges. The calcium carbonate, that is a non-electrolyte, I'm not changing it at all. I'm going to leave it as it is as I bring it down. Now, when I break these into their ions, we have to leave it balanced, which means calcium chloride is made up of 3 ions, 1 calcium, a chloride, and then another chloride. Sodium carbonate is made up of a sodium, and a carbonate. And sodium carbonate. And the sodium chloride is made up of a sodium and a chloride. But I do have to keep track of that coefficient of a 2. So this is what it looks like when I break these 3 apart. So calcium chloride became calcium ion and 2 chloride ions. That subscript became a coefficient because this is actually 3 pieces. Sodium carbonate became sodium ion and carbonate ion. Now, the 2 subscript right there became a 2 right there. The reason why the 3 subscript did not become a 3 out front, the polyatomic ions stay together. So you needed to recognize CO3 is a carbonate polyatomic ion, so you leave it as CO3. Calcium carbonate does not change. It just goes directly down, okay, because it's a non-electrolyte. Sodium chloride is becomes sodium ion and chloride ion. That 2 goes in front of both of them. Okay, so this equation should still be balanced. So I need to make sure everything that's an ion, it has a charge. Yep. Not an ion. Yep. Everything has a state of matter. Aqueous, solid, aqueous. Awesome. And that everything should still be balanced. 1 calcium, 2 chlorides, 2 sodiums, 1 carbonate. Awesome. That would be my ionic equation. So now, to move on to my net ionic equation, I need to look for spectator ions and cancel them out. So when I look for spectator ions, my first ion here is calcium 2 plus aqueous. I look on the product side. I do not see anything that looks exactly like calcium 2 plus aqueous. So not a spectator ion. 2 Cl minus aqueous. 2 Cl minus aqueous. 2 Cl minus aqueous. That's a spectator ion. I can cancel it out. 2 sodium plus aqueous. 2 sodium plus aqueous. That's a spectator ion. I can cancel that out. CO3 2 minus aqueous. Well, shoot. So what I have left is my net ionic equation. So I'm going to go ahead and rewrite that. The things I canceled out are gone. The things that I did not cancel out are what I'm rewriting. Calcium ion, aqueous, and carbonate ion, aqueous, arrow, calcium carbonate solid. That's my net ionic equation. I want you guys to try this one. So why don't you go ahead and hit pause. Try identifying the strong electrolytes, writing the ionic equation, and then converting it to the net ionic equation, and then we'll go through it together. This is our last example for this video, but we are going to do more examples as we move through the rest of chapter 4. Okay, so now we need to identify the strong electrolytes. So first I look for the 7 strong acids. There are no acids at all. Okay. Next I look for the 8 strong bases. None of the 8 strong bases are present. You can refer back to the chart that has the 7 strong acids and the 8 strong bases listed when you're doing this for right now. Next is to look for soluble ionic compounds. Well, everything is an ionic compound because it's made up of a positive charge and a negative charge. So the soluble ionic compounds are the ionic compounds that are aqueous. So all 4 of them are ionic compounds. 3 of the 4 are aqueous. So strong electrolyte, non-electrolyte, strong electrolyte. Okay, so when I break this apart, I'm going to take those 3 compounds that are strong electrolytes and dissociate them into their ions, making sure to keep everything balanced. The one compound that is a non-electrolyte will not change. It will look exactly the same. So 3 silver nitrates become 3 silver ions and 3 nitrate ions. Potassium phosphate becomes 3 potassiums and 1 phosphate. Silver phosphate doesn't change. 3 potassium nitrates become 3 potassiums and 3 nitrates, so it looks like this. Silver nitrate, when I broke it into its ions, looks like this. Potassium phosphate, when I broke it into its ions, looks like that. This one didn't change at all. And then the potassium nitrate, well, it goes down to the other side, but that's what we have. That would be my ionic equation. Now, to get it to the net ionic equation, we're looking for spectator ions. So 3 Ag plus aqueous. That's not what I see over here. 3 NO3 minus aqueous. 3 NO3 minus aqueous. I know that was weird because it went to the other line, but those are the same. 3K plus aqueous, 3K plus aqueous. They're cross. PO4 3 minus aqueous. I don't see that on the other side. So the things that are left that I didn't cancel out, I will rewrite them. 3 Ag plus aqueous plus phosphate, aqueous, arrow, silver phosphate solid. So we just went from a molecular equation to an ionic equation to a net ionic equation.